Good evening once again. It doesn't seem like 5 minutes since we were last here talking to each other. So this is the second talk for this evening on ancient light. In the previous talk I talked about relatively short lengths of time, what happens in 1 second. Here I'm talking about a journey which has taken most of the lifetime of the universe to complete. So it started with a lockdown challenge. Back in 2020, life as we knew it, of course, changed. Life in lockdown, when this particular object gave rise to a lot of these objects all over the floors and pavements of various buildings and supermarkets and other areas. We were continually told to separate ourselves from other people, and we got this message, keep your distance. When I looked at these footprints on the floor, I thought of Stephen Hawking's comment, remember to look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. So I thought, okay, I'm not going to let lockdown get me down. I'm not going to look down at my feet. I'm going to look up, and I'm going to look up as far as I can. How far could that possibly be? So that was the origin of the lockdown challenge. We know, of course, that the universe is vast and is ancient, and we know that large telescopes have imaged galaxies that are billions of light years distant. The question I asked myself was, is it possible to capture an image of one of these very remote objects on the edge of the observable universe? Is it possible to capture an image of one of these without using a telescope? Spoiler alert, yes it is. That's what I'm talking about here. So I started by reading a paper published in 2019 that catalogued a whole load of quasars. What is a quasar? A quasar is the nucleus of a galaxy that emits enough radiation, enough visible light, in order to be seen at tremendous distances, billions of light years. What is actually producing all of that light? Well, we think a quasar is essentially a supermassive black hole which is feeding rather voraciously. In other words, a lot of matter is falling into the supermassive black hole, and as that matter falls in, it generates a huge amount of energy and a huge amount of radiation. Some of it might come out in jets, as indicated by this artist's impression. We don't understand all of the mechanism of what's going on inside a quasar or in the area around a quasar, but we do know they generate enormous amounts of energy. So in this particular case, I looked at this catalogue of very luminous quasars, and I picked one that should be visible from the UK during the summer. This was the summer of 2020. I wanted one that was high in the sky so I could easily photograph it. And I found one of the quasars in their survey that fitted the bill of being high in the sky in the UK summer, and its spectrum doesn't look particularly spectacular. This is the spectrum that they obtained. Here we're looking at the intensity of light from the blue to the red end of the spectrum. The numbers here are the wavelengths in angstroms. 1 angstrom is 1/10 of a nanometer, for those that prefer to work in nanometers. And although this isn't a very spectacular spectrum, they recognise that this particular bump here is actually supposed to be in the ultraviolet part of the spectrum. In other words, if you had a source of light which was not moving relative to you, then that bump would occur in the ultraviolet part of the spectrum at a wavelength of 1200 angstroms. But here we see it at 6500 angstroms, which means it's been shifted from a low value to a high value. It's been pushed towards the right. It's been redshifted. Why does light get redshifted when it comes from remote objects? Well, that's because the universe is expanding. So as the light travels from the object when it's emitted to being received by us, it's travelling through space, which is expanding, and that stretches out the wavelength. The more distant the object, the more the wavelength gets stretched, the greater the redshift, in other words. We quantify the redshift by looking at where would the wavelength appear in a spectrum if the object wasn't moving, in this case 1200, and where does it appear for this particular object, in this case 6500. we take the second minus the first and divide it by the first. In other words, for this particular object, 6500 minus 1200 is 5300. That's the change in the wavelength. Divide that by the original wavelength and we get a redshift of 4 and a bit, 4.3. So that's how we quantify redshift. It's a dimensionless number which gives us an indication of the distance to the object. A redshift of over 4 means that this quasar is very remote, and I'll talk about the distance and how we calculate the distance in a few slides' time. But this was the most distant object, the largest redshift object that I could find in their catalogue that would be visible from the UK. There were a few others, but only visible from the southern hemisphere. So I grabbed my trusty camera. This is the camera I use for pretty much everything, astrophotography as well as taking pictures of animals. I grabbed my camera, put it on top of a star tracker. So this white box here is basically just a box with some batteries and a motor, which will turn the camera at 1 revolution per day in order to follow the stars, providing the tracker is lined up with the Earth's axis. So the tracker has this little polar scope built into it, as I'm sure some of you have got equatorial mounts with a polar scope in the right ascension axis. So this polar scope allowed me to line up this tracker and then switch it on, and it would then move the camera at 1 revolution per day. My camera is, as indicated here, it's a Nikon camera with a 300mm f4 lens. Now, this particular combination of the camera with the lens, these are not in any way customized or modified for astrophotography. They are precisely the same camera and lens that I use for wildlife photography, for instance. So if a camera and lens that's designed to take pictures in daylight, if it's capable of taking pictures of zebras, can that same combination of photographic gear be used to photograph a quasar many billions of light years away? Okay, I decided where I was going to point the camera by looking up the position of this particular quasar that I've got my eye on. It's in the constellation of Draco, and the little rectangle there on the left hand side shows the field of view of a 300mm lens superimposed on the constellation of Draco, and there's Ursa Minor and of course Polaris on the right hand side. So this particular patch of sky is almost overhead during the middle of the summer. In the middle of that rectangle there's a little dot. No, that's not the quasar. The quasar is much fainter than you can see in this star map. That star happens to be a 5th magnitude star, which is not far away from the quasar in terms of its line of sight. That was rather convenient for me because I could line up my camera on that star and know that the quasar was in the same field of view. So there's the picture I ended up taking with that 5th magnitude star in the middle there. I wanted to expose for as long as possible. This is the middle of the summer, and of course you don't get much night time in the middle of the summer. You just get a little bit of time between twilights. And so I took images for about 2 hours, but rather than take one long exposure, I took a series of shorter exposures because some clouds were scudding by. So I took over 100 short exposures, and then afterwards threw away those frames that had clouds scudding by and took all the frames that appeared to be clear sky and added them all together to give me the equivalent of a 2-hour exposure. I expected the quasar to be right next door to that 5th magnitude star. So I looked there on my final image, blew it up, and by checking with plate solving to double check I was looking in the right place, I determined that that is the object I was looking for. That is the quasar with a redshift of 4.3. So most of the light from the quasar is focused into just 1 pixel of the image. If I blow that up on the left hand side so you can see the individual pixels of the image, you can see that most of the light from the quasar has been focused into 1 pixel. I've exaggerated some of the fainter pixels there just a little bit so you can see other features and a little bit of noise in the background. So the original camera is a 20 megapixel image, and I've really zoomed in here just to show you that the quasar is indeed imaged correctly. In terms of what resolution can we expect from the lens and the camera, simply by knowing the aperture, a 300mm lens focal length with an f4 means that the aperture is about 75mm, so we can calculate what the expected resolution would be, assuming the lens is perfect. This particular lens wasn't cheap, so I hope it has no aberrations that would give rise to any resolution that's worse than this. We would expect the resolution to be about 9 microradians, millionths of a radian. If you want that in arc seconds, that's a little bit less than 2 arc seconds. Perhaps comparable to the scene on that particular evening. If we look at how far apart the pixels are in a 20 megapixel sensor for the Nikon camera, they are about 15 microradians apart, or that's equivalent to a resolution of order 3 arc seconds. So the resolution of the lens and the resolution of the camera are reasonably close to each other. And just for a point of reference, if we imagine how big would the Milky Way be if it was at the same distance as this particular quasar, it would be a couple of pixels or so on the image. So returning to that particular crop from the centre of the image, what I'm laughingly calling the Barrett Deep Field here, when I looked at that to confirm that I was indeed imaging the quasar, I also noticed that there were other objects in the field of view, some of which are stars, but some of them are not stars. I checked the 8x8 arc minute crop that I'm showing you there, and by checking against reference images from research telescopes, I determined that a number of these objects are actually galaxies. Some of them you can sort of tell are galaxies because they're not circular, they're a little bit elongated, which tends to be the case when you're looking at elliptical galaxies or sometimes spiral galaxies. Some of those objects I'm sure you cannot tell, and I couldn't tell that they were stars purely by looking at them. It's only by comparing with a research image that I could tell that those 10 objects were galaxies. So in this small crop, I've managed to catch 10 galaxies plus the quasar itself, which is in the centre of a galaxy. If the whole image is anything like that, and there's no reason to assume that I wouldn't get something similar if I took a crop from a different part of the image, that means that this particular 2-hour image has probably captured about 7,000 galaxies. It's sobering to realise that with a camera and a telephoto lens, you can probably take a picture with as many galaxies in it as in, for instance, the Hubble Deep Field. I'm not claiming this picture is as good, but it's interesting to note that you can pick up thousands of galaxies one way or the other. So let's return to this idea of, okay, it's a distant object with a high redshift, but what is the distance to this object? Light left this galaxy a long time ago, and we can think about how far is it, or how far was it from the Earth to this galaxy when the light left. And then we can say, well, as the light was travelling from the galaxy to Earth, because it took such a long time, the universe continued to expand. So whilst the light is travelling, the galaxy is getting further away. And by the time the light arrives at Earth, the galaxy is even further away from Earth. So you can think of that as the distance when the light left, the distance then, and the distance now that the light has arrived. So the middle one is a representation of how far the light has travelled. But you can ask, well, the distance then, or the distance now, or the distance the light has travelled, these are all 3 different distances. Which is the correct value to use for the distance? Well, actually, there's no such thing. You can't define the distance. You have to specify whether you're talking about the distance when the light left, the distance now the light has arrived, or the distance the light has travelled. Quite often people use the middle one, the distance the light has travelled. But that's rather tricky to actually define. Because when you think about it, the light is travelling through space at the same time that space is expanding. Just because the light left the galaxy, well, space doesn't know that. It will still continue to expand as the universe expands. So light is travelling through space at the same time that space is expanding. So trying to work out how far the light has travelled is actually quite tricky. It's like imagining somebody swimming through water and the water is moving. In some cases, the water might be moving faster than the swimmer can actually swim. It's another analogy is to think about an ant moving along a rubber band. You can imagine an ant moving, and if you know its speed, you can work out how far the ant has travelled. But what if somebody, whilst the ant is walking, what if somebody is stretching the rubber band? Then trying to work out how far has the ant moved at the same time that you are stretching the rubber band is quite tricky. The bottom line is we cannot measure the distance to a remote object like a distant galaxy. We can't measure the distance directly. We can't measure the length of time it's taken the light to arrive. We know that it's travelling at the speed of light. If we know how long it takes, we can work out that distance. But we don't know the distance, we cannot measure it, and we don't know the time. We cannot measure it. There's only actually one thing we can measure with very distant objects. And that comes back to what I mentioned earlier. We can measure the redshift. And that is the only thing that we've got to work with. So we have to rely on the fact that if we can measure the redshift, if I'm looking at that distant object, I can look at its spectrum and work out how much the features have moved, how much they've been shifted to the red end of the spectrum. I can then say, well, if I've got a particular redshift, if I think I understand how the universe is expanding, and more importantly, how the universe has been expanding for the last few billion years, if I've got a good idea of how that's happened, then I can work out for a given redshift how far must that object be from us. In other words, I have to have a reasonable guess as to what the universe is doing before I can convert a redshift, which I can measure, to a distance which I can calculate. And that's what these three curves here are. I've taken the best guess for what we think the universe has been doing. In other words, if we work out how much matter there is in the universe and include things like dark matter and dark energy, we can get an estimate of how we think the universe has been expanding since the Big Bang. I put those numbers into a spreadsheet, and this is what I calculated. For a given redshift, we can calculate how far the object must have been when the light left. That's the blue line, the distance then. We can work out how far the light would have travelled from leaving the object to arriving at Earth. That's the green line, the light travel distance. And we can work out, now that the light has arrived from this distant object, how far away is that object now? That's the red line, the distance now. So those are based on a particular model. If the model of the universe changes, then those lines might change slightly. But that's the best guess that I could come up with based on the best guess of cosmology. So let's have a look at our quasar. Our quasar is at a redshift of 4.3, so we get three numbers out of that. And those are the three numbers there. Let's just remove the curves because we're not interested in redshift of other objects at the moment. Let's remove the curves and just leave ourselves with those three numbers. So that means for this quasar which I've imaged, the light left the object when it was 5 billion light years away. So the distance from the Earth to the quasar was 5 billion light years when the light left the quasar. The light from the quasar has been travelling for over 12 billion years. Remember that the universe age is approximately 13.8 billion years. So that means the light has been travelling for something like 90% of the age of the universe in order to get from the quasar to Earth. And finally, during that time, whilst the light was on its way from the quasar to Earth, the universe continued to expand, and so the quasar got even further away. And so now the quasar is some 25 billion light years away. Big numbers. But it's interesting to note that the quasar was 5 billion light years away and is now 25 billion light years away. It's increased its distance from Earth by about 20 billion light years, but it's done it over a time period of only 12 billion years. So if we do a quick back of the envelope calculation, The light travel time of 12 billion years, during that time the quasar distance increased by 20, i.e. more than 12 billion light years. So we can work out an average distance. We can work out an average speed as distance over time. It's changed by 20 billion light years over a time period of 12 billion years, which means the average speed of recession of this particular quasar is more than 1.5 times the speed of light. It was moving away from us faster than the speed of light when the light left, and it's moving away from us faster than the speed of light now. Again, using our idea of how the universe has expanded, we can actually calculate the numbers. And it turns out that for this object, when the light left the quasar was receding from us at over twice the speed of light. And it's still moving at nearly that, 1.7. But notice that after initially slowing down a bit, this is velocity as a function of time here, Big Bang on the left, now on the right, the velocity at which this object is receding from us, it started slowing down for quite a few billion years. But as of somewhere around 7 billion years or so after the Big Bang, it started to accelerate again. So it initially slowed down, presumably because the expansion of the universe was being slowed by gravity. But for the last few billion years, its velocity away from us has been increasing. It's accelerating. The universe expansion is accelerating. This was a surprise which was discovered 20 or so years ago, and we think the accelerating expansion of the universe is a result of what we are now labeling dark energy. We don't really understand what it is, but that's the label that we're giving it. And I think it's interesting to note that we can see that in this curve. It starts slowing down, but then it picks up again. Let's think about the journey that the light has taken. Here I've got a graph of time since the Big Bang in the vertical axis and distance from us in billions of light years on the horizontal axis. So here's the quasar about 4.5 billion, some 5 billion light years from us when the light left. Not at the Big Bang itself, which is this bottom left-hand corner, but after something like 1.5 billion years after the Big Bang, that's when the quasar emitted the light that we've just detected. So we might imagine, what has the light done? Well, it's got closer and closer and closer to us. In other words, the distance has got smaller and smaller and smaller as time goes. Remember, time is the vertical axis here. There's us here and now at the top. So we might imagine that the light has followed that green arrow. But no, because in the early days, the quasar was receding from us faster than light. In other words, the light was trying to make its way to us, but because space was expanding faster than that, the light from the quasar was travelling through space that was expanding faster than it could travel, like a swimmer swimming through water where the water was pushing the swimmer back faster than the swimmer could swim. Or an ant was moving along a rubber band and the rubber band was being stretched faster than the ant could walk, so the ant gets carried backwards. So that's what actually happened in this situation. It's rather bizarre to think about, but in the very early days, for the first few billion years, the distance from the light to us increased. Even though the light is trying to get to us, the distance from the light to Earth actually increased from 4.5 to 5 to nearly 6 billion light years. And eventually the light managed to overcome the expansion of the universe and started to make some headway towards us. So it's a really odd looking curve. You don't really expect to see these things, and it's odd looking simply because we're not used to thinking about the idea of living in a universe which is expanding. It doesn't really apply to us on a day-to-day basis, but it does when you're talking about things happening over billions of light years, over billions of years. So the light started travelling backwards and eventually made it to us here and now, 13.8 billion years after the Big Bang. If we imagine what happened to the quasar, that's the journey the light took in green. What did the quasar do? Well, the quasar just got carried along by the expanding universe. The universe continued to expand, and so the distance from the quasar to us simply continued to increase as time went by. So the light eventually made it to us. The quasar is now at some 25 billion light years distance. I've shown it as a dotted line simply because I didn't want to draw it as a solid line. Remember, I showed you the velocity in the previous slide. The velocity changes during the light's journey. So in other words, sometimes it was going faster, sometimes it was going slower, then it got faster again. So this ought to be a slightly wavy line, and I couldn't work out exactly what shape it was supposed to be, so I'm just indicating, roughly speaking, the quasar started at 5 billion light years from us and is now some 25 billion light years from us. 12 billion years later. Let's just finish with thinking about the journey as seen from the light. The light was emitted by the quasar 1.4 billion years after the Big Bang. It had already been travelling for some 8 billion years before even the Sun and the Earth were born. And thereafter it continued its journey for another 4.5 billion years. The Earth formed, life evolved on Earth, and the light continued its journey. Dinosaurs came and went, the light travelled on. In the last million years of its journey, the light arrived at the edge of the Milky Way, crossed a spiral arm or two, entered the solar system. In the last few hours, it would have arrived at Earth. It would have travelled through the atmosphere in a fraction of a second, hurtled towards England, dodged a few clouds at the last minute, and then entered the lens and hit the camera sensor. Just a pixel in the 20 megapixel image. But what a journey it's had. Here's a graphical summary of what I've been talking about. I put my camera on a tracker. The bottom left inset shows the camera on a star tracker, rotating the camera 1 revolution per day. I pointed the camera in the constellation of Draco, as shown by the top left inset, and that shows in the main panel, the star in the middle is the star 80 Draco, a 5th magnitude star. But just to the right of that, as shown by the top right inset and shown by the grey lines, is the quasar that I photographed at a redshift of Z equals 4. It took 12 billion years for the light to arrive, 90% of the age of the universe, and that object is now 25 billion light years away. So yes, without using a telescope, it is possible to catch what I like to think of as the quasar's ancient light. Thank you all for listening.